Hello everyone. Today we are going to study the propagation of ultrasound. The main points of this section are 1. The propagation speed of ultrasonic waves. 2. The attenuation of the ultrasonic waves. On the evening of June the 70th, 2020, after a magnitude 6 earthquake occurred in Changning County, Yibin, Sichuan. An earthquake warning signal was received in Chengdu, where is more than 300 kilometers away. This warning signal arrived in Chengdu about 60 seconds earlier than the seismic wave. In fact, since the Wenchuan earthquake, the development of China's earthquake science and technology can be described as earth-shaking, and good progress has been made in basic research, surveying, engineering technology, and other fields. At present, we can issue an early warning 6 seconds after an earthquake occurs at the epicenter, which is the best speed in the world. Do you know how it works? Look at the propagation speed of the ultrasonic waves. Ultrasonic waves, like other mechanical waves, rely on the vibration of the medium particles and the elastic force between the particles when propagating in the medium. Therefore, the propagation speed of the ultrasonic waves in the medium is affected by the physical properties of the medium itself and has different propagation speeds in different media. Generally speaking, the propagation speed of ultrasonic waves in the medium is related to the ultrasonic wave type, the elastic modulus and the density of the medium, and the temperature during propagation. 1. Propagation speed in solid medium. In a solid medium, not only longitudinal waves, but also transverse waves and surface waves can be propagated. In solid media of different shapes and sizes, their sound velocities are different, which will be discussed separately below. In the first case, the speed of sound in an infinite solid medium. The infinite solid medium here means that the size of the solid medium is much larger than the wavelength of the ultrasonic wave, and the echo reflected from the interface can be ignored. In this case, the sound velocities of longitudinal waves, shear waves, and surface waves are respectively, where E is the Young's modulus of elasticity of the medium, ρ is the density of the medium, and mu is the Poisson's ratio of the medium. It can be found from the formula that as the density of the medium increases, the propagation velocity of the ultrasonic wave decreases. The elastic modulus increases and the propagation velocity of the ultrasonic wave increases. In the same solid medium, the speed of the sound longitudinal wave, shear wave, and surface wave is different. In turn, the propagation velocity of longitudinal wave is greater than that of shear waves, and the propagation velocity of shear waves is greater than that of surface waves. For steel commonly used in ultrasonic testing, the longitudinal wave velocity CL is approximately equal to 1.8 8 times the shear wave velocity cs, and the shear wave velocity cs is approximately equal to 1.1 times the surface wave velocity. The second case, the speed of sound in a slender rod. It is only related to elastic modulus and density. It can be seen from the above formula that the propagation speed of a tronic wave in a solid is mainly related to the density and elastic modulus of the solid medium. In fact, the speed of sound in the medium is also affected by these factors. 1. The temperature of the medium, usually solid. The speed of sound decreases with increasing temperature. Using this feature, it can be used for the non-resolving measurement of the medium temperature and can be further used for the measurement of the melting point, boiling point, and phase transition of the medium. 2. The state of the material structure. Usually the sound velocity of fine-grained materials is greater than that of coarse-grained materials. The graphite content and size in cast iron increase, and the speed of the sound decreases. 3. In the state of stress, the stress of the general material increases and the speed of sound increases, but the growth rate is slow and the compressive stress increases the speed of sound. When an earthquake occurs, the epicenter also emits longitudinal and transverse waves, but the seismic waves are infrasound waves. However, its propagation law is the same as that of the ultrasonic waves, and the propagation velocity of longitudinal waves is also greater than that of transverse waves in the same medium. Using this velocity difference, we can quickly calculate the focal depths through simple calculations and use electromagnetic wave signals to implement early warning. As shown in the figure, the longitudinal wave velocity of the seismic wave emitted by the source A is 7,000 m/s, and the transverse wave velocity is 3,000 m/s. The focal depth h is 10 kilometers and L1 is 100 kilometers. When the seismic wave is received at point B, it immediately sends an earthquake signal to point C to seek advance warning time. The calculation expressions of focal depths and early warning time can be obtained by single mathematical derivation. In the formula, delta t is the time difference between the longitudinal wave L and the transverse wave S from point A of the source to point B on the Earth's surface. Bringing in the known data, it is calculated that the seismic wave will not reach the point C until about 13 seconds after the point C on the Earth's surface receives the early warning signal of the point B. That is, a 13-second early warning is achieved. 2. The speed of sound in liquids and gases. The velocity of ultrasonic waves in liquids and gases is smaller to the velocity of sound in slender rod solids, except that the elastic modulus of the solid is replaced by the bulk modulus. The speed of sound in the liquid medium is also affected by temperature. For all liquids except water, as the temperature increases, the bulk modulus decreases and the speed of sound decreases. In water, the speed of sound reaches a maximum when the temperature is around 76 centigrade. Second, the attenuation of ultrasonic wave. We know that propagation process of ultrasonic waves is completed by the elastic force between the particles in the medium, and the vibration of each particle is driven by the adjacent previous particle. The vibration from the energy of the previous particle are transmitted to the next particle like a drum. During this process, a part of the energy will be dissipated in the form of heat due to the internal friction between the particles. In addition, when the ultrasonic wave hits the heterogeneous interface, it will also produce reflection, refraction, etc., resulting in the gradual decrease of the sound energy per unit area in its main propagation direction. This phenomena is called the attenuation of the ultrasonic wave. To sum up, there are two main reasons for its attenuation. 1. In the process of ultrasonic wave propagation, due to reflection and scattering, part of its sound energy deviates from its propagation direction, resulting in a decrease in sound energy in the detection direction. 2. The absorption of the medium converts a part of the sound energy into another kind of energy, often thermal energy, which reduces the sound intensity. Usually, we divide the attenuation method of ultrasonic waves into the following three categories. 1. Sound beam diffusion attenuation. The ultrasonic wave spreads cross-sectionally on the propagation path, so that the energy of the ultrasonic wave per unit area gradually decreases. Diffusion attenuation. In theory, there is no diffusion of plane waves, so there is no diffusion attenuation. The beam of the cylindrical wave spreads around, and its energy is inversely proportional to the propagation distance, that is, I infinity 1/x. The beam of the spherical wave spreads in all directions, and its energy is inversely proportional to the propagation distance, that is, I infinite 1/x to above. 2. Sound beam scattering attenuation. Scattering means that during the propagation of ultrasonic waves, it encounters heterogeneous interfaces with different acoustic impedances, resulting in chaotic reflection and refraction, resulting in a decrease in energy in the main propagation direction. This method is called scattering attenuation. During the ultrasonic testing process, if the grains of the material are relatively coarse, the ultrasonic waves will be scattered on the grain boundaries obviously, which will cause the ultrasonic waves to propagate to the probe along a complicated path, and the forest-like echo will appear in the display screen as shown in the figure. 3. Dielectric absorption attenuation. During the propagation of the ultrasonic waves, due to the vibration of the medium particles, mutual internal friction and heat conduction, the ultrasonic energy is attenuated, which is called absorption attenuation. In addition to the 3 main attenuation methods, there are also attenuation caused by dislocations, magnetic domains, residual stresses, etc. The attenuation in actual ultrasonic testing mainly refers to absorption attenuation and scattering attenuation, and use the attenuation coefficient. Alpha indicates its attenuation degree. The unit is dB/millimeter. That is, alpha is equal to alpha S below plus alpha X below multiplied by alpha S below, and alpha X below represent the scattering attenuation coefficient and absorption attenuation coefficient, respectively, which are related to the properties of the material and ultrasonic frequency. In the formula given, D is the Lagrange size, usually between 0.015 and 0.25 mm. F is the anisotropy coefficient of the material, and C is the coefficient. It can be seen from the formula. 1. The absorption attenuation of the medium is proportional to the frequency of the ultrasonic waves. 2. The scattering attenuation of the medium is related to F, D, and F, and is greatly affected by the frequency F. In actual ultrasonic testing, if the crystal grains of the material are large and the frequency is too high, it will cause serious attenuation. This is one of the difficulties in ultrasonic testing of large grain, austenitic steels, and some castings. For liquid media, the attenuation of the medium is mainly absorption attenuation. In the formula, mu is the viscosity, a coefficient of the medium. C is the wave speed. Since mu, rho, and C are called related to temperature, the attenuation coefficient alpha is also related to temperature. Generally, alpha decreases with the increase of temperature, which is beneficial to the propagation of ultrasonic waves. How is the attenuation coefficient determined? According to the stipulations in the currently commonly used standard MB/T 47,013 to 2,015, the measurement of the attenuation coefficient of the workpiece is divided into 2 cases. One is that the thickness of the workpiece is less than 3 times the near field area, and the other is that the thickness of the workpiece is not less than 3 times the near field area. For the first case, as shown in the figure, takes 2 non-adjacent bottom waves and calculates according to the given formula, where Bm and Bn refer to the mth and nth bottom wave heights respectively, and m and n are integer greater than 1. When the workpiece thickness T is greater than or equal to 3 times the near field area, the following formula is used to calculate. The main difference between these two measurement methods is, in the first case, due to the short sound path, the height difference between the 2 adjacent bottom waves is not obvious, so the adjacent bottom waves are not used for measurement. For the second case, the sound path is usually larger, and the ultrasonic diffusion is obvious, and its influence must be considered. Finally, it should be noted that the measurement of the attenuation coefficient should be carried out in the intact area of the workpiece without defects, and measured 3 times according to the above method, and the average value is used as the final attenuation coefficient value. In actual ultrasonic testing, the debugging of the instrument is often carried out on the comparison test block. According to the provisions of the standard NT/T 47013 to 2015, when the material attenuation coefficient difference between the workpiece and the comparison test block exceeds 4 dB/m, it must be make corrections. Therefore, the measurement of ultrasonic attenuation coefficient is an essential step. That's all for today. Thanks for your watching.